I know you didn't, but.
I only have 3 subjects.
All right, so here we go. Nice to have you again. Lecture 3. Let's see. So this lecture 3, let's have the door so that. Let's see the animation. Animation is to help us. All right. Lecture 3. Sort of continuation of wave-particle duality, in that we now take our conclusion, the uncertainty principle that we saw from the full wave property, well specified, and localization challenge. Doing both will lead to uncertainties in wave-like properties as well as particulate properties. So now the solution for particles that are exhibiting wave-like properties and for waves exhibiting particulate properties is to construct a wave function that contains these two extremes: wave properties, particulate properties. In other words, you want a wave function that has a wave that can be sort of localized. That is why today is wave packet. A wave packet does that. Look, the animation. It's a wave. You can see the waves. But there is a packet, a Gaussian packet, that sort of localizes it, and you can get the probability of where it is. It's cool. It's a Gaussian wave packet. There could be other wave packets, but a Gaussian wave packet does the job almost perfectly. It is the wave function of minimum uncertainty. It's cool. That's what we want to do. So connect from last time. And quick question, just to challenge people a little bit from what they've done before and from what you've read. What's the difference between the animation on the left and the animation on the right? Yes, please.
The left one, the normalized?
I'm sorry?
The left one normalized?
The left one, your claim is that it is, okay, let's assume both are normalized, because both are normalizable. Good point. They will not be normalizable if they remain wave all the way to infinity. But they have gone down, yeah? The wave function has gone to 0 as the position goes out to positive infinity and negative infinity. Are we together? So good idea, but there are difference between animation here and yes, please.
Well, the one on the right looks like it has momentum to it. So could you be more certain about the position on the left and the momentum on the right?
Yeah, you have the idea momentum. You've said something about momentum, which is wave number. Yeah, because P is h bar k. So here the wave number is now like a function of time. So that's very technical. But can you make it even less technical by just looking so that anybody watching this out there can actually see the difference you're talking about? It's obvious. It's showing what is it about the wave packet here and the wave packet here? Yes, yeah.
The wave packet on the right is like changing.
Exactly, it is changing. Correct. And from your hand, the description on your hand, we call that sort of change a dispersion. The wave packet on the right is dispersing. It means that it is evolving. And hopefully, according to the time-dependent Schrdinger equation. And this is the wave packet. It's doing what it should do. It's waving, but it is not evolving in time. There is no dispersion. So we have the math to handle wave functions that represent particles behaving as waves and waves behaving as particles. We're fortunate. That's the lecture today. So, some reminders, and was that cut across who wanted his quiz back?
That is correct.
I do have your quiz back. Thank you for pointing. Now I know that I've done something nice by putting it to you on time. James, Melanie, Topka, you're over there. Millie is here. Grace is over here. Yeah, Qatar. You're welcome. Hannah, where are you? Over there. Alan. So good job, everyone.
Thank you.
Yeah.
I had a question about that. On the blue line, the quiz was out of 10, but it looks like you graded them out of 5.
Oh, I'm sorry. I'll fix that. Yeah. That's because I teach another course that is out of 5. I teach radiation biophysics. It's getting in.
Understandable.
Yes, thank you so much. Now I still admit that I'm yet to make the distinction between Joey and Joe.
I'm Joe.
Okay, thank you, Joe. And then Joey. Yes, thank you. All right, good job, everyone. Can we then take a few announcements and then the quiz? So, return today. Quiz 2 today, homework solutions posted. So that you can look at your work and then I'll get back your scripts on Thursday. Is that okay? Then, I hope this is fine with you. Homework 2 is due. So let's see how far we go. And if people have issues, you can meet me. I have my time there, the office hours. But look, it says feel free to come to my office whenever I'm there. So, yeah, in addition. So let's talk, let's help people. Then in the syllabus, you will see other resources. Let's say we are talking and quickly doing Gaussian integrals and you are not very familiar with it, or you've forgotten it's a long time you did it, then my resources in the syllabus, there are many, suggest certain little nice books that can handle certain mathematical tools. And on that, you see, your preface of the book kind of hinted why we need the mathematical tools. Who remembers the analogy in the preface about what would happen if we don't have the math tools to do quantum mechanics, the good math tools? Yes. So Joey is... I'm sorry?
It's on the tip of my tongue, I can't think.
Yeah, Carter?
Is it like you could still do it, it would just be harder?
Exactly, that's the message. It will be very hard, and the analogy was memorable. It will be like a dentist extracting your tooth with pliers. I don't want my teeth to be extracted with pliers. Honest, I don't. So I'm going to learn the math. I'm going to do my best to show you the math, the nitty-gritty detail, but we cannot do all in class. So there are some resources in the syllabus that I have suggested so that we can handle that, okay? So let's do the quiz. We have week 4 already out there, so you know exactly what comes next on blue line. And we won't use that today. Quiz 2. if you're ready. Thank you. Okay. Thank you, James. Thank you, Amelie.
Got my name on this.
Oh, yeah. Good. Are we all done, please? Did I get from everyone? Seems so. Yes, thank you. So we continue and we can show what the solutions are straightforward. So it says, let me see if I can use my all right. Preserves normalization. So integral negative infinity, positive infinity. If you like, you can write psi star. Okay. All of it you want. Okay. Write down the expectation value of momentum. Yeah. We claim that once we have psi of x comma t, we can get all the dynamical variables. This is one nice case. So expectation value of momentum can be expressed as, so mv is momentum, mass times velocity in the case of a particle. So velocity is, let's put it this way. So the expectation value of the velocity, okay? Integral can be written nicely this way. Negative I h bar partial x, okay? You can put it very conspicuously so that you know what it is. It is actually an operator. It shows clearly that if indeed you find psi, you can calculate other dynamical quantities such as the momentum. And the steps to do that, you see, we need to be able to get momentum in order to get standard deviation of momentum, in order to get Heisenberg uncertainty principle, all that. So, if the steps required to go there are not clear to us, I'm going to start back here. Oh, which one is it? Okay, so we're fine. So if the steps, we were talking about getting the expectation value of the momentum, and I can go forward. We need the expectation value of the momentum in order to calculate the standard deviation of the momentum and the standard deviation of position in order to get Heisenberg's uncertainty principle. Does that make sense? And the steps in calculating these other dynamical variables involve some tricks, some simple math with the Schrodinger equation. And the beginning in your book of showing such simple math is in proving that once normalized, the wave function stays normalized. Another expression for what you saw in the reading section, I think 1.4, the normalization. Another expression for that is the conservation of probability. So we will be using it a lot. It is in showing that once normalized, the wave function stays normalized, that we see the math steps in deriving that expression for momentum that we just saw, which is I bar partial x. Yeah. So I'm going to show you on the board all that because, well, without pretending, it is so important, as you heard, even in the reading, that here is what can become a question in exam 1, for instance. Prove that once normalized, the wave function stays normalized. We actually need to know all the steps and actually do it conveniently, comfortably, and convincingly. So let's connect what we want to do. I'm going to repeat myself a little bit just to make sure that everyone is following. From last lecture, we saw statistics behind standard deviation and how to put that together in terms of position and momentum due to the wave-particle duality of stuff. Electrons behaving like waves, electromagnetic waves, photons behaving like particles. So, the uncertainty principle. And how can we localize a wave? How can we enwave a particle? The Gaussian wave packet. We saw that last time. And I'm going to repeat that. And to get us there, the steps in calculating and showing this involve nice, interesting stuff that we pick up even from our text, right from here, right from the normalization. So steps for calculation of dynamical variables, position, momentum, and therefore their uncertainties assume the conservation of probability. That is, once normalized, the wave function stays normalized. And we want to prove it explicitly on the board. Is that okay? Ready? Good. I can see eager, ready. Quantum mechanics students. So I'll leave this here so that we see what's going on. So when you did it last time, you kind of zoomed in and it was clear. Awesome. So now I can be guided by what you have.
You should get up there.
Okay. Let's see how much I have. Yeah. Not bad. Right. So today we will have a long, so let's say, what should we call it? Heisenberg uncertainty principle, wave packet, but we want to learn some things through normalization. Okay. What was the number of the last equation we did last time?
15.
15? So let's do 16 and say we want to prove. There are many ways of saying what we want to do. We can say that psi of x comma t star Let's conjugate dx equals 1. So it stays normalized. So how do we prove that it stays normalized? Is to show that the time derivative, here please. Oh yeah, I like the answer.
Oh.
Go for it. Yes.
You take the time derivative of that.
Thank you. Awesome. Yeah, let's call it the grace step there. Yes. Any answer, we name the step after you. After all, we've been saying Schrdinger equation. That's how it all begins, right? The grace step. Yes. To take the time derivative, dt, and prove that. Can I just write it in a short form, right? Please. Thank you. So dx.
What's the difference between those again? I forget. Why is it different when you
It's
square
right
it?
there. This is the absolute value, which is an easy way to calculate this too,
Like they're like totally interchangeable, right?
to a very large extent.
Okay.
Yes. Because this will allow, this often allows us to just take one of them and square.
Yeah.
Knowing that that will be the result. Good.
Is there a time that you wouldn't want to just square it?
Yes.
Okay.
Because in general, good question, in general, psi is complex valued.
Yeah.
And if it is a psi that has physical meaning, this is true. But you could think of functions that this is not true.
Okay.
In other words, they are described as non-integrable functions. You cannot integrate them, But in general, for quantum mechanics, this is true. Okay. So time derivative, we have it right there. And what should it be?
0.
Very good. So can we put a question mark there to understand that we want to prove it? Put a question mark right there. So what are we going to do? Watch carefully. We are going to do what Griffiths did in terms of writing this d dt integral negative infinity to positive infinity of psi x, the full wave function squared dx, and we'll have to justify it and understand why that is correct. Negative infinity, positive infinity. We take the partial derivative from the full time derivative over here, it becomes partial derivative inside here. And what is the reason? Anybody?
Because there's x and t inside there, so you only want to take it with respect to t, so it's partial.
Again, so that everyone can hear.
Because there's, like, the weight function is in terms of x and t, so
Correct.
you only want to take it in terms of t.
Exactly, because the integrand, the wave function, is a function of position, explicit function of position and time. We take partial derivative. Yeah, so that so those aspects. Which then allows us to go to step 2. How do we calculate that? What can we call step 2? I want to take this out and express it.
Product rule.
Sorry?
You can use the product rule to.
Exactly, the product rule. And now the Joey product rule. The Joe product rule. The Joe. Yes. That's clump, right?
It's Jared.
Oh, sorry, that's clump. Sorry, mixed up. So
Okay, we
the
got a lot of
Jared-
J's right here.
Yes. So the Jared product rule gets applied here. Good job. So let's do that quickly. Partial t. Write it explicitly so that we do not mix up anything. Just this. See, please watch just this part. I have my blue stuff here. Just this part. This part out there. So let's write it. And it becomes what? Psi star partial psi partial t plus The book puts the other constant, this one on the right, I don't like it. I like to put my constants here. So that when I'm calculating, I do not mistakenly take derivative again of my, what should be constant, okay? But the book is fine, it's consistent. So, right, we got that. And here is where we enjoy the Schrodinger equation, because we can now use the Schrodinger equation to make things easy for ourselves. Let me do it here. What do we call that step then? Where we apply the time-dependent Schrodinger equation. We can apply it. Okay, tell us what to do. At least qualitatively. Anybody?
Would you
Raise
set
again. Okay, Carter this time.
would you set the derivatives equal to the time like they're in the Schrodinger equation?
Exactly, you got it. So the Carter step is get the time-dependent Schrodinger equation involved. Yeah, because you've got this psi dt, and that's okay. Let's write it. I h bar partial psi partial t equals what according to time-dependent Schrodinger equation? Negative h bar squared over 2m partial squared psi partial x squared plus v psi. Are we happy with that? Okay. Now, these are the things I wanted to make explicit. Divide this by I h bar, and that means you also get I h bar over here, and you also get 1 over I h bar over here. What do we get? So these go away, can you see? And partial psi, partial t becomes what? We don't like i's downstairs. What do we do to get rid of the I upstairs, downstairs?
You multiply by I over I.
Yes, so I times I, negative 1, right? And then that kicks out that negative. And then there's h bar here, kicks out 1 h bar. Do you agree that we end up with h bar, with I h bar over 2m, partial squared psi, partial x squared, plus, what do we do here? We don't want the I downstairs. So I times I downstairs, minus. Then there is 1 I there because we did I over I, yeah? So what do we end up with? Minus what? Minus I over h bar t psi. Good. Any question? All right. So quickly, we get the complex conjugate. Why? Because we have a complex conjugate formula. So what will it be? Negative, because it's complex conjugate, right? So negative I h bar over 2m. What else? Partial squared psi partial x squared, and it has to be a complex conjugate. The negative becomes what?
Positive.
Very good. I v. So I over h bar psi star. This is good because we will use this repeatedly. Look, we're going to use this repeatedly in calculations. That's why we do it. So what's the next step in proving what we wanted to prove? We've done step 3, the Carter step of getting the time-dependent Schrodinger equation. Okay, the great step, the general step. So what's the next step? Now that we have our expressions for the time derivatives of the wave function and its complex conjugate, what do we do? Substitute. Yeah, the substitution. So who gets the credit now? Yeah, you can't do it twice. Who agrees with him then?
Could be the Jared
Okay,
featuring
so
Grace.
Tucker agrees with him.
Well done, Tucker.
So the Tucker, can I wipe this side, please? Tucker step then. Step 4. Tucker substitution step, I think. So, what does he want to substitute? Thank you. Yeah, what are we to substitute? We got those. So, we had partial psi, partial t squared to prove. You remember? And we said that it was equal to partial psi star, partial, yeah, so psi star right there. Let's put it psi star plus psi, partial psi. Check for me, is that okay? All right, so we can now substitute and say that this guy is equal to psi star. We bring in this. Is that okay? I h bar over 2m partial squared psi partial x squared. Look, in order to not waste more time, by the time we make the addition, this will cancel this. Yeah? Okay, you all agree nicely. So we can just simplify things then. We've got our psi star for this. This. Okay? And what we need, since this will go with that, so this will go with this, we can then do this part plus like psi partial, so we're taking this chunk. And that chunk, yes, is a negative. Yeah? And if you like, you can take that IH bar over 2m, which is over there, see? See the IH bar over 2m is there in both of them. It's there here, it's also here. So I'm going to do it faster because you can follow. I saw your eyes showing that. So I'm going to put the IH bar over here, over 2m, and put my psi star. Yes, put this psi star right there. You see what I'm doing? This psi star is right here. And now the d psi dt that survives this is here. Is that okay? You got it. This that survives is here. And we can now subtract. Put bracket. Now subtract. Get that one. Psi, so d squared psi dt dx squared. I'm missing something deliberately, so let me see how we are following. There's something wrong there. I've left one mistake there. Who can catch it? Yes, Millie?
The second term in both
This term?
or the v psi.
Yeah, they cancelled out. We already did that. Yeah, good idea, but they cancelled out because we were adding. Yeah, there is no derivative with them, so they cancelled out. Yes, please.
It should be partial squared psi star.
Excellent. That's what I left. To see how you're feeling. Good job. Hey, nice. Okay. You know, there's some other crazy trick we can do, which Griffiths also did. And and you will see why shortly. It is getting this partial derivative, this Laplacian in one dimension, separating them. And you can do that because remember, in handling the product rule, you were treating this as a constant and this as a constant. So you can carry on that product rule argument and say, and open this up into partial x, yeah, into I h bar, what we have right now, 2m, yes, psi star, partial psi, partial x, minus psi, partial psi star, partial x. And you can then close. Anybody having issues with that? And here is the reason. That should be the last step of our. Yeah. I wonder where to write it. The reason we do this is to make the integration easy for us. Okay, so I'm going to do it over here. Step number 5. Let me do it over here. Step number 5. So watch it so that we can kind of recapitulate. We wanted to show that. So partial t of psi squared dx equals what? And we just calculated this guy here. Is that okay? So we have just calculated the whole of this thing. Yeah. We just did this thing. And it is this. Is that okay? Can we now put it in, please? We just calculated this term is this term. Can we put it in? Good. So it means integral partial x I h bar over 2m into psi star partial psi partial x minus psi partial psi star partial x. Should be equal to something. I'm missing something again. Who fixes it? I deliberately left something away.
dx.
dx, thank you, Carter. And we do something that some mathematicians don't like. And we do it and get, yes, please?
Shouldn't there be a dt on the left side?
On here?
Yeah.
Good question. That's exactly why we're doing this in class, so that we see every step. Anybody can answer that question?
Oh, it's okay.
Oh yeah, Millie answers her question.
Oh, it's just from the substitution.
Yes, from the substitution. Good check. Yes, any other one? Any other self-check? All right, so Carter fixed that for us. Now we're going to do that thing that physicists do a lot and get away with it because it works. It's accurate.
Yeah. Dr. Christian's like that.
You know what I mean, right?
Yeah,
So now we've got our dx equals x, right? Plus some constant. So this is equal to I h bar over 2m psi star partial psi partial x minus psi partial psi partial x evaluated at negative infinity and positive infinity. And here is the crucial argument that as x goes to plus or minus infinity, psi and its first derivative, if you like, partial psi, partial t, should go to what? 0. Why? Why?
Because otherwise it's not a wave function.
Otherwise,
It's not normalized.
you guys have succeeded in making you real physicists, but I know that some of you are also math majors. So I want you to be good math majors and good physicists. Otherwise, it is still a wave function, but not normalizable. It retains its mathematical properties, but it doesn't solve the physics situation. Is it? I think it is clear. I don't need to ask. I could see it from your faces. So that's why the normalizable solutions are what we work with in physics. And yes,
When you're looking at that and you decide that x is going to infinity, how do you think of that like as going to 0? Like where are you plugging infinity into? Or is that just it has to be true?
oh, we're saying, remember psi is a function of x. So psi is on the y-axis, x is this way. And the square of psi will give us the probability on the y-axis. So as you're going, since it is a function of x, as you're going to positive infinity, negative infinity, it is going down here. Otherwise, you cannot localize it.
Yeah.
Because localizing it means it peaks somewhere. And if it peaks somewhere, it must be 0 somewhere else. Yep. Good point. Any other question? Or all right. So we got this argument that precisely because as for physically realizable wave function, which since physicists are also good mathematicians, they now create a space of wave functions that have the right physical properties and call it a space of square integrable function. And if you like big words, you can call it a space of quadratically integrable functions. Isn't that sounding? And some people call it the Lebesgue space. And we can call it, well, some functions in Hilbert space. We will get to that in chapter 3. Anyway, that allows us to put this finally as equal to what?
0.
Once normalized, the wave function stays normalized. And we have spent some time playing the games that we do to solve many problems. Let's see how we're doing with time. I wanted to go quickly to the part that has to do with Heisenberg uncertainty principle. I can do that in 2 steps and then we take a break. Is that okay? Yeah, it will be very summarized, so we take a break. If you have all this written down, can I wipe the board? Thank you.
Three whole seconds.
World changing.
So, what we are saying is, this is a wave,
James is a math purist.
one extreme, another extreme.
Don't help us.
Let me make it below what we did last time. So a Gaussian. We can write this as psi of x comma t equals a e to the I kx minus omega t. You know this. It's a plane wave. The other extreme, a Gaussian. Yeah? Gaussian function. Is this normalizable? Plane wave?
Yes.
No, because it's not 0 to infinity.
Yes, it will blow up at positive and negative infinity.
Oh.
Uh-huh.
Yep.
Great. And to represent real particles that exist somewhere, meaning that their position, no matter how probable or spread out, is somewhere. Localizable and also with wave-like properties, we come up with something in between. A Gaussian wave packet, and that is what it is like. Ha ha ha! That's the whole thing there. So this in between is what we started out with. Gaussian wave packet, so we have 1 over square root of 2 pi, something like that. Integral g of k e to I kx minus omega t. Yeah? We can allow the Gaussian envelope to specify the properties of the momentum or momenta, while the spread, yeah, is in terms of x, the properties of the wave, the plane wave. And we can use this Gaussian wave packet, which is this one, in its explicit form, to calculate sigma x, yeah, which we did last time on the slides, and found it to be something like, I think it was a square root of 2. We will look at it again on my slides. And we can also calculate sigma sub k, because we've got the k's here, the Fourier integral. And it ends up, as you saw on my slides, as we will see again, 1 over a times square root of 2. We'll look at that again. But remember, P equals h bar k, which means that sigma P should be equal to h bar sigma k. Do you agree? Because h bar is a constant. Do you agree? Good. So then, and a big one, sigma x, sigma p, precisely p sub x, should be equal to a over square root of 2 times, look at sigma p, h bar sigma k. So h bar over a root 2. What is this equal to? Everybody.
H bar over 2.
What is it equal to?
R over 2.
Can you see me now? I'm oscillating like a wave particle. What is it equal to? H bar over 2. That is the minimum uncertainty. That is the origin of the uncertainty principle. This is the best we can do. So a wave packet, a Gaussian wave packet, is a wave function of minimum uncertainty. And we will prove it in subsequent, I think it should be chapter 3. With this, we take a break.